Alrighty then, happy Tuesday afternoon. We're going into the second part of the marine ice sheet instability hypothesis. The analysis, traditionally the second part of any one of these units or lessons is something about analysis. And we've done math stuff and we've done a variety of exercise to sharpen your skills. The one today is totally different in the sense that we'll work on another set of skills. And basically what I want you to do is come down and make a decision, whether this is a viable hypothesis or the competing hypothesis is better. In the end, it's about two different feedbacks. The marine ice sheet instability talks about a positive feedback. It's going to run out of control, the world's going to go destroyed, and everybody's dead. Not quite that sincere. Everybody in the coastal thing. I'm going to introduce some lines of evidence that suggest that may not be true today. And your analysis for this is kind of trying to pick and choose between those two possibilities. It's an analysis of reading information and then making a decision, which is mostly what we do in life. Before I get going any further, or might there be any questions? All right. Let's get it out of the way then. This is a complex system. It's an ongoing debate. I'm going to ask you to come down one side of a decision of a question that the scientific community has not come up with, weighed in A or B. So there you go. We won't be prejudiced by what they think. So the recent example was, okay, I'm going to start off with a little digression to a past lesson, talk about calving, and then talk about this a little bit, then introduce, and this should be out-headed here, a negative feedback. We'll call it uplift for the sake of argument. And your assignment is to weigh in two sides of that debate. The backtrack a little bit is this notion of a paper that just came out this week, is this notion about under what conditions are humans not comfortable, but can they survive? As you all might imagine, there's a certain temperature which humans don't do very well at. In fact, they die. It turns out that from a medical perspective, the human body, not only is temperature, but humidity is a big deal. So there are people who study this a lot. And so this is an example of greatly enhanced risk to humans as a consequence of a lot of terms here. Basically, it's about heat stress. Some combination of temperature and humidity that the body doesn't do so well in. For example, they talk about what's called the wet bulb temperature, which isn't strictly the temperature, and then down here they have some things about the absolute temperature and then the percentages. And what you see is we do fine up to, this is theoretically how hot it can get, but basically most folks that they've measured this on don't make it too much beyond here. And then as it gets hotter and more humid, I think, I might be misreading this, the survivability drops off. So this is all medicine, and I don't pretend to fully understand all of it, but the notion is, I think we can all understand that heat and humidity, not so comfortable, but it also can be fatal. So let's start with reading what they have to say in their simplified version. So go ahead and read the first sentence if you would, please. Go, keep going.
Here we incorporate our laboratory measured physiologically based wet bulb temperature thresholds across a range of air temperatures and relative humidities to project future heat stress risk from bias corrected model output.
All right, what does that translate to in English? That's the English summary, that's not the technical summary. Give me your view of what that just said.
The heat and humidity that they tested, they basically tested in a laboratory, I'm guessing?
No, they have tested on humans. But they start off with an opening sentence. Heat's not good for you. That's fine, right? So now we've got a problem identified. The next sentence, we do something. What did they do? all this stuff, right? What did they do once they assessed all of that to project what?
Future heat, stress, risk.
How much at risk are you going to be because it gets warmer, right? And where did they get the heat values?
They got the heat values tests.
From bias corrected, whoever knows what that means, climate model output. In other words, they get them from some predictions. So that limits its usefulness because who knows if the predictions are right. But they cover a range of bases, so it's going to be somewhat right. So go ahead and pick up with the next sentence. So why do we really care about this? Read it if you would.
These vulnerability thresholds sustainably increase the calculated risk of widespread, potentially dangerous, uncompromisable humidity, heat, stress.
What does that mean? There's some value that if you cross it, it gets bad for you, right? You want to read the next paragraph, next sentence? Oh, so that's all sort of, that's the finding. Now what they did is apply it to different places, because that's where it gets interesting. Go ahead.
Some of the most populated regions, typically lower middle income countries in the moist tropics and subtropics, violate this.
I like the word violate, you know. Okay,
Violate this threshold well before 3 degrees Celsius of warming.
okay, fine. What does that mean?
That's like,
This- Go ahead.
that like some different countries, like,
They don't say where, but they say some places, some regions,
yeah.
happen to be the most populated. Okay. Typically in low-income families, or low-income countries, in the where it's humid. What do you mean? What's violate? Why did I get all excited about violate? Well before. Go ahead.
Yeah, I'm just trying to think of another word to use besides violate. Like,
Well, these folks violate or something about this threshold. They run up against it.
yeah, like cross.
Or they can't do it under certain conditions. And then what is a certain condition?
Well before 3 degrees Celsius.
Well before 3 degrees Celsius. So if the world is actually going to have a 4-degree thing, these folks are kind of interesting. Okay. Lady next to her, would you want to finish it off, please?
Further global warming increases the extent of threshold crossing into drier regions, for example, in North America and the Middle East. These differentiated patterns imply vastly different heat adaptation strategies, limiting warming to under 2 degrees Celsius nearly eliminates this risk.
Okay, so forget the last sentence for now, but what did most of the rest of this say? Further global warming beyond 3 degrees increases what? They talk about certain regions here, and then they say it gets warmer than that. Increases the chance of violating the threshold for these geographical areas. Oh, there's one of interest. These different. Then they say, because you're in so many different geographical areas, your ways to adapt to it might differ. And then the interesting last line. So this is a great problem. But if you stay under 2 degrees, not a problem. So we just read a technical summary of paper. We digested it in little pieces, and we got a lot of information out of it. I like looking at the graphical part, so this is the graphical thing. what they have are their risks. It's not quite total risk, it's how many hot hours that you have, and I forget which period of time. Annual hot hours, annual things where it's going to be bad for you, for a temperature rise of 1.5, 2, 3, and 4 degrees. They don't really know how hot it's going to get. So they did this calculation for various regions, and this is by geographical region. Lady in back, pick out where would you worry about this heat risk the most? If you were, a UN official and you had to decide where you want to tackle this problem. What colors do you want to look for to find the worst places? The red is. And also not just the red, but how much red there is, right? Where's the most red on that thing? Through northern India, through eastern China, and it's through a lot of eastern and southern Africa, Saudi Arabia. A lot of red in the US? Not so much. Does that mean we're okay? All right, why not? Oh, there's a little bit of red there. No. We may not be at threat by this particular mechanism as much as other people, but there's a lot of folks. Okay, so this is the kind of paper that comes out a lot to try to figure out what we're going to do or how we can come out of global warming. I'm going to shift gears very abruptly now. We're going to go back to the marine instability argument, which is all about sea level. Before I go fully on that, one of the things that evaluating the work this morning that we noticed was the last question, which was about what does it matter about sea level rate? Last lesson was about just some mythical sea level rise over a given time. What we're worried about this time is how fast can that happen? And so I think there's several of you that got a thing that said, if sea level rises, I don't remember what it said, a meter in 100 years versus 10 years, would that matter? Yeah, how fast it comes in, by putting that rate in the term, that's the problem I was worried about. So we can tidy that little question up. All right, shall we bludgeon forth? Calving we saw this pretty picture the other day, but basically this is the meltwater pool setting on top of a glacier that, because the water is denser than the ice, have a tendency to go down through it, and this is what blew up the Lawson ice shelf. Basically, it got warm, and here it is. Here's a little place in Antarctica. This is out on the fingertips, the Antarctic Peninsula. Here's the ice shelf before. This is the other part of the peninsula. This other black is the water. So there's a mountain range in here. There's glaciers flowing into here and forming this ice shelf. And it's only 50 kilometers across, which is sort of the size of Hamilton County. But then this is what it normally looks like. Then one satellite pool in the austral summer showed all of a sudden dark spots, which were exactly like the blue on the last picture. And there was a lot of blue spots. And how could you get melting water on top of ice?
The
top.
energy gathers in pools because it doesn't reflect as much.
That's a feedback that would extenuate the thing, but how do you get it started? In other words, you're down here where it's cold all the time, snowy. All of a sudden you got melty. What has to change? It's a big flat white surface. It's the simplest way to melt snow.
The salt?
Should I have bought into the commission of the salt trucks that delivered all of that? air temperature. An area that's not generally susceptible to warm air temperatures had a warm summer, and all of a sudden there's all these pools of water around here. The pools of water had a tendency to sink down through the ice, and mechanically started breaking it apart. So the next satellite pass is all these little pieces of ice. So we lost something on the order of a little over 50 kilometers within a month. It disintegrated, blew up, and most of you got that, most of you found the area. The tricky part of this, it was floating, so there was no change in sea level by breaking all these pieces of ice up. Some of you found a little bit related incident in the sense that all of these glaciers are moving kind of slow because they run into this buttressing effect. Pull the plug, these things will speed up, and since these glaciers are above the sea level, they're going to drain down. They're talking about a couple millimeters, I think, of effect from this. This isn't a very big area, it turns out, but you know, you're not going to see it overnight. But what you're going to see is this one's going to break up. That left a little piece here, and then there's a couple more of these ice. There's another ice shelf that's blown too. All right, so that's the Larsen B. The threat of the marine instability hypothesis really hinges on this map. This is the map of Antarctica, of the topography, both above the orange colors and below sea level. So it extends beyond. We were just there, so it's a little spot in Antarctica. And so the blue colors, and to some extent the green colors, are below sea level. All right, so what we kept drawing last time we talked about this was a glacier that comes down something like this, and sea level's here, right? And we were worried about the fact that the base slopes down, because that's what gave us the positive feedback. Gentleman back in the cap. Here's Pine Island Bay and Thwaites Glacier, right? So how do you interpret this big blue area in here? Excuse me?
Different than the eastern side, like entirely, since it's blue instead of yellow.
It's different. And how is it different? These yellows and blues are contrasting features of what?
It's a lower temperature.
Not the lower temperature, this is topography, elevation. And so where's the magic line of 0 implies the greens and these greens at least, and the blues are what, below or above sea level?
The blues are below sea level.
So this is an ice mass now with ice far above sea level. If we started the runaway effect here, where's it going to end?
At the bottom of where it's zero.
Why wouldn't it? Why? So here? Well, it's going to keep rolling through that, right? Because there's still going to be this flotation thing. And the argument is that really should gut out this whole thing. So this is the size of Texas. Remember, this is the ice shelf that's floating. And that's not going to matter. There's another ice shelf over here. But all of a sudden, it's this matter plus the residual ice going in. That's the 4 meters or 3 meters of sea level rise. And this is why this is so vulnerable a place. Here, you can't get through the mountains. Here, you can't get through the mountains. Here, you seem to be stuck up. Nobody's too worried about it. Right there is the weak underbelly, what Mercer would call the weak underbelly of the Antarctic ice sheet. That's where you don't want the thing to start. That's exactly where Thwaites Glacier is. So this should have been included in the last lecture, but here we are. At least we picked it up in that. The buttressing, we've made reference to it. Basically, it's jamming. It's a jamming effect. All these glaciers flow into each other here, and they tie each other up. Pull this plug, just like Larsen B, that's Larsen B, and the flow of these would all accelerate. So if you pull this plug, Pine Island Thwaites, you're going to start gutting out that. Okay, there's a buttress effect there. It's relatively small compared to these, but it's pretty good sized. All right, so the plug is pulled. That's what we need to worry about. So people have been studying these two glaciers intensively to figure out if the plug is being pulled. So here's a pretty color map of this is Pine Island. I'm using them kind of interchangeably, but that's all right. Here's the speed, and this is showing that convergence effect. And one thing that's important in here is the grounding line, the white line. Out here it's all floating. This is up against land. It's not flowing too fast, it's converging here, so it's floating there. So the grounding line's position then becomes of interest. Why would I care about where the grounding line's doing? Where it starts floating, the equivalent of this right here.
Because as you go further back, you're getting more ice.
More ice flexing out.
Yeah.
But also if I'm on this slope going backwards,
And it's a positive feedback.
that's the positive feedback. So one could argue that you just want to track, it doesn't matter where the ice is, the ice, edge of the ice. You see the nice satellite photos of the edge of the ice, but it's this spot that's more critical to monitor. And that's what this study did with a variety of satellite images. So 0 is up here at the top of this figure, and these are the speeds, and you don't need to worry about all of them. The general pattern is this. And so what we see is in the last sort of bit of the thing, it's floating. It's all the same speed because it just flows out as a big plug. Right here is the transition zone where it starts picking up speed. So yeah, it gets a little bit faster, a little bit faster, a little bit faster, picks up, and then it slows down. Faster speed, but it slows down. So that's what it looks like in space. The other side of the equation is what does it happen over time? 10 years, which is not very long for these systems. These systems take a long time. And so first point is that there's the blue and black are from water stations out here where they measure the water temperature. Gentlemen way in back. What's the water temperature doing as you go from 2010 to 2020? From both stations. It's kind of bouncing around here, and then all of a sudden it takes off warmer, right? So what would we expect if they're warming? Is warming going to be a problem in here? Why would we care about why would they bother to put a station in there? Say again, please. This is actually ocean. This is the ocean temperature. So this is going to be melting underneath here, which sort of is the same one or the other. You can thin it both ways. And then this is the actual grounding line, and it turns around. It's not really doing much. It bounces around a little bit, but it's not doing much. So this is a graphical representation of this process. This is a measurement of the thing. 4,000 meters a year is pretty fast glacier flow. 4 kilometers. Okay, so another study, there's that same squiggly white line. They worried about where the ice was breaking up. And so you walk through time, 5 years ago, 8 years ago, whatever 23 and 17 is, through different months. And so what you see is the big pieces breaking off. Do we necessarily care about the pieces that are breaking off the end? Yes or no?
We don't really need to care about it right after, but maybe.
We don't need to worry too much about them?
I mean, right after it breaks.
Right after it breaks. The sea level is not going to go up because they're floating, right? but the buttressing thing. So this is jammed in here. So this can't, all the flow from the other graph is jammed in here. Now I'm going to take a little piece away. I'm going to take another piece away. I'm going to put another piece away. Would we worry about that? In other words, this is slowed down in part because this is plugged up here, right? Now I'm going to take that piece away, and I'm going to take that piece away, and I'm going to take that piece away. Does that do anything to the mechanics of the flow? If we,
That will cause some other related disasters.
yeah, because this is not plugging this up. The buttressing is removed, it's going to come out faster. So it's going to resupply with more velocity, or that's the anticipation. That would be what we observed at the Lawson B example that we saw. That's what happens. It's starting to speed up now. It took a decade for it to speed up. This one hasn't really triggered yet, and it'll probably take a decade or more to pick up. But this is part of the, if that picks up and it goes back and it's irreversible, we're doomed kind of story. Okay, so is the long term, is the braking or portion of the grounding line more important? Is it this part of the exercise that's more important, or this position that's more important? Lady in red.
Can you say that again?
Excuse me?
Can you say that again?
I'm asking sort of there's two processes going on here. One of them is this thing, which is sort of this position, or this moving of the buttress, which ultimately could affect things if it goes on. Which one, if you had money to measure one of these, because you're going to try to, you were charged with predicting it, but you only could measure one, would you measure the position of this or this position? It's not a yes or no question, is it? This is the kind of questions that I'm starting to ask this week. We're going to be hesitant to jump into a question, but there's no right answer to it, so don't worry about it. Which would you put your money towards? Would you try to monitor this or try to monitor this? Because they're different things. No, but see, this is the problem. We set up a challenge where it's one or the other, because life is, restricted by how much money you can spend. They are measuring both, of course. But hypothetically, if you had to pick one. The grounding line? The grounding line, because this is where, when this starts going, you're in trouble. But this is a mechanism that could be, it doesn't signal that it's going, but this is going to increase the chances it could. So that's a question. And that's only 5 years of record, so there's pretty dramatic changes there, but the grounding line hasn't done anything yet. Okay. So we worry about melting from the bottom. We blew up Lawson B by melting from the top. These areas right now are too far south to get serious. It's not as likely as you're going to melt the surface. It's not impossible. Lawson B is way out here. These are further south, colder. But what is of concern is what underneath. So this is a little clip of, is going to zoom in on here, and here's the temperature. Basically, the reds to blues are some representation of the temperature of the melting. How much water is actually being melted. And so it's just, I've got it more for an interesting graphic to see the side of this thing. There's a lot of vertical exaggeration here. There's the big East Antarctic ice sheet. Here's a representation of the currents. The currents are going in here and coming out here. There's a lot of currents attacking this coast. Doesn't matter. There's mountain chain there defending it. We're going to rotate around to our buddy Pine Island Bay right there, where it's not able to defend itself, basically. So this little video then is useful for our purposes, not there. Clunk, clunk. Here's mountain chains to defend it, mountain chains to defend it. smaller mountain chains, but here's the gateway into the bottom of the West Antarctic ice sheet. Okay. All right, so I'm just trying to give you some pressure on this. So we're about, this is a much larger view. We've talked about ocean currents. We've talked about how complex they are. This is even more complex. Here's Antarctica. Here's Australia. Here's the Pacific side up to Alaska. And this would be the Atlantic side towards the South America tip. What the take-home message here is the water circulates on the surface around and around because the wind keeps going around and around. These deeper bodies of water, the turning points that we were talking about, these are part of the circulation patterns that go. And you can see when we talked about the AMOC, it was like one overturning. And here they've got, I don't know, 1, 2, 3, 4, 5, thermohaline water, 1, 2, 3, 4, 5, 6, 7 different bodies of water all doing the same trick. So it's a little more complex. That's the take-home message. But these are of concern because this is what's supplying the warm water. Or not. All right, we're almost done with, so this is the better conceptual model than my drawing. We're going to leave it for now. We've talked all we're going to talk about that hypothesis for, well, I got one more graph, sorry. Any questions on this so far? All of that, those are elements that we've all talked about, right? Possibly warming on the top, warming on the bottom, breaking it off, having a complex topography, melting, glacier coming this way. Here's the water in a little drone. This is from, one of the studies they did. Makes perfect sense? Doable sense? Okay. That's this diagram here. Step A, step B, step C. There's a slight variant of it that basically says you get rid of all of this, and then you get a vertical cliff. And the vertical cliff then melts. This is a variant on the theme. For our purposes, they're the same. I'm not going to make a big deal about the differences here because it's got a different name, and it's going to tell you that instead of having the ice shelf, you're going to go to this model, but then the retreat continues. So that's fine. All right, enough of that. In the sense, there's the summary diagram. Is there any point I should add or expand upon? This is what most people perceive this whole hypothesis is about. It's been around, a lot of people have studied it not to death, but most of the studying, very little of it is actual measurements because we haven't known about it. You can't get measurements. Most of it is mathematical modelings. If it works, it's going to be a meter of sea level in your lifetime. It's going to be faster than the 1 meter in 100 centuries, in the century. Unless you all live to be much older than I think you're going to live. The real problem, that's only 1 meter of the 4 or 5 that's there. The real problem is going to be further down the road. And then as a philosophical side, do you care about what's down the road 300 or 400 years? I don't know. As geologists, we always worry about timescales of that length, but not necessarily do we need, it's not the kind of decision we can make easily. All right, switching gears. Technical paper, bunch of fancy things. Basically, this is going to describe the possibility of the mechanism of a feedback loop. We're going to have a couple lines of evidence that suggest that this mechanisms that work. Basically, it's only been discovered for a year or two, and it has to do with the crust. Right in that little thin belt that's the soft underbelly, it's a volcanic region. Volcanic crust is warm, and therefore it's less dense. Therefore, it's not as rigid. And so what we discovered, I didn't discover, but in the last decade or so, they started measuring, here's Pine Island Glacier, they started measuring how fast the crust is coming up. if it's relative sea level that's important, you can get away with bringing the crust up and therefore effectively making it shallow. So there's two feedbacks here. By taking the glacier off, if the crust comes back up fast enough, it'll keep the thing in check. If it doesn't come up fast enough, you got the runaway. And so the data here suggests uplift rates, and there's a range of them, but they're sort of in the that much a year, which is pretty fast uplift. Nobody that I know of, I'm sure somebody has at this point, done the modeling to say, is that enough to prevent this? So we only have it for 10 years, but and there's a couple people up at Ohio State that are involved in this. And so what this is saying is, if you're here and you calculate that at this rate, it's going to raise up Antarctica quite a bit, maybe shutting the thing off. So here's a mechanism. It's a viable mechanism. Nobody knows the answer yet, whether it's going to kick her off or off. So one other mechanism that we have to look is, besides the modeling of it, which would be, I'm sure is being done someplace, is we can look back in a longer term geologic record and see if the ice sheet has decayed itself in the past and then reconstructed, decayed, reconstructed, or not. If it's come and gone, come and gone, come and gone, it's likely to go again. If it hasn't gone for a long period of time, it may not go again. That's a qualitative argument, I get it. So there's a study that looked at this several years ago, and they went to a mountain range right here, which isn't exactly, Pine Island Bay is actually over here, but this is a mountain range adjacent to this ice shelf, and here's what the mountains look like, basically. One of the features in Antarctica is what's called a trim line, and that represents a place where the glaciers, that was the maximum extent of glaciers at some time in the past. Glaciers got up that thick. You have little spirally peaks, very, very Swiss looking, and you have subdued peaks below them. So what they wanted to do was measure the last time those peaks were exposed. So if the ice sheet were unstable, they should get young ages, and they should recollect a time when it collapsed. If the ice sheet were more stable, the ages in here should be old. So far, that makes sense? Okay. And here's a cross section of it. Here's the mountains underneath the ice sheet, and here's the dipstick that they're going to measure. There's one particular set of, it's called Independent Hills. That's one Nunatak they called, or Patriot Hills over here. All right. This is what it looks like in block view. The A, B, and C, well, let's start in the backwards. I don't know if it's better. Let's go from A to B. The ice flow's coming out here. There's that hill. That's the Nunatak. Here's the trim line. And just because ice sheets flow down, it would have come over this at one point, but now it thins around it. And so you could go to, that's what it looks like today. Theoretically, here's that trim line. The ice was up there. That's a model, thick ice. This is a model of it having collapsed. So the trim line would be high and dry. So the key is the age of these things, either stability or instability. Their results are exposure ages in thousands of years. So 1,000 is how many? About 1 million, yeah. Okay, so this is 1 million years. That's 1 million, there's 2. Here's the elevation that they've got samples from different elevations. So you want to decide between whether the thing was up here and it went down to there, or it just went down a little bit. These ages at 2 different elevations suggest how long has it been, when was the last time that it changed elevations dramatically. something in which number? This time at this time. There's no ages out here, but there's a lot of ages from, that's 1250,000. So that's 1.25 million, right? So has this thing decayed down in here in, say, the last 1,250,000 years? That's the way that's the interpretation that you could be made. There are people who would argue against it, but the interpretation is that this is pretty stable, hasn't done anything. So here's, despite the theoretical reasons to fear this, you look at the geologic record and you get a different answer. Who are you going to believe? This is your homework assignment. Okay? Ice sheet's been stable for 1.4 million years or something. All right, why is it? It's back to the thin crust rises. So it effectively makes sea level shallower, which is coming up. All right, I'm done with new material, I think. Yes. I want to walk through exactly what I'm asking you to do for the assignment. It's not that complicated. You're going to gnarl your teeth and gash your teeth over this a little bit, but that's okay. Wear off the plaque. I'm going to about 2 or 3 slides to walk through this. So this is it. This is an exercise in you considering 2 sides of the science argument with 2 lines of evidence that seem to conflict. Scientists are doing this all the time. Who do you want to believe? I want to give you just enough taste that you can get into it and come down one way or the other on this particular argument, because it's a skill development. There's no right answer. Nobody knows the exact answer, so you can't be wrong. That's a positive feedback loop. This is a negative feedback loop. One of them's got to win in the long run. Stability, instability. It turns out that there are people who are suggesting, wait, this is such a problem, we need to worry about stopping it. That turns out to be an expensive proposition, and we'll worry about that on Thursday. Today, the primary decision is whether it's the positive or the negative is which will win. So you can couch it as positive or negative. That difference is important if you wanted to plan for it. If it's negative feedback wins, you don't have to plan for it. You can worry about something else. If the positive feedback wins, you need to worry about it. All right, specifically, I would say there's some non-traditional resources available to you. I've actually broken it down into these 2 categories, and I've provided on Canvas some papers, some technical papers. You don't have to go looking for them. You're welcome to go look for the public presses on these. These are the technical papers. And there's quite a few more papers on this than on this. I'd like you to look at least 2 from each category. They may give you slightly different answers. And they should be inside a folder that's called links to all folders. Do you get when you download the lecture notes, do you get them from the modules unit? Okay, in the modules there's today's thing, and then there's also a link to papers, right? Yeah, is that what it's called, links to the papers?
I'll check that.
Thank you.
Yeah.
Okay, and if you click on that link, you'll get a whole bunch of folders. Excuse me, they're all listed, right?
Yes.
They're
It's instability for
yeah, I should have set this up. So all right, there's papers there for the instability and the other, and there's a bunch of other papers. Okay. You could go further with information, but I think if you just look at 2 of these things, that'll get you be enough. Science questions usually aren't settled in the court of public opinion. All right, that's part of the point here. How do you do this? these papers are in what we call the primary literature. They're technical, they're gobbledygook, they're buried in obscurity, and you need the passwords of the high priest to get into them. Because they're all written in the same book way. There's ways to attack it. Look at the title very carefully. What does that tell you? That will tell you the point of the paper. The next thing is to read the first summary, the abstract, or the written summary. There'll be about a paragraph, just like the one we read today in class. It'll have 90% of what you need to get out of the paper right there. It'll be tough to read, and you can skip some of the big words. If that isn't enough, then don't read the paper. You won't be able to, the terms will be nonsense. But you can go to the end of the paper. The end of the paper, they try to summarize it again, and the end of the paper will tell you why it's important. I always look at the pretty pictures, because I can get 80% of 90% out of the paper right from the figures, unless it's poorly written. Forget the rest of it. Get yourself an look at 4 papers. You don't have to read them. 2 pro, 2 con, 2 stability, 2 other. Look at the arguments. Which one do you put more weight in? Pick a side, and just develop the point. So far, so good. So this focuses you to talk a little bit about that side. This focuses you to talk about this side, instability, stability side. Here's the gnarly one, which side, and then why it's important. The why it's important will vary a little bit depending on which side you take. Maxine, any questions? Straightforward. We're going to dig into the literature. If everybody that's online wants to find the papers, they're not arranged by titles. You're going to have to click on the title, on the author's name. So at some point you should list which papers you use for both sides. Do that up in here. Okay? Just so I know which papers you did. All right. Shall we adjourn? Why don't I formally cut down the lecture, but I'll stay here. If you want to dive into those, which some people are doing, then we can make great progress, because I'll help you. Otherwise, we'll see you on Thursday.